Alright, so let's now put everything we've talked about in this chapter together and look at how we sketch the curves of graphs without using a calculator, using everything that we know. So for the first one, for f of x equal to 1 over x squared minus 1, with f prime of x equals negative 2x over x squared minus 1 quantity squared, and f double prime of x equals 2 times 3x squared plus 1 over x squared minus 1 to the third power, let's find the following. So the first thing we want to find is our domain. So remember, to find the domain, you want to set the denominator of f of x equal to 0. So in this case, x squared minus 1 equals 0. So that factors as x plus 1 times x minus 1 equal to 0, which then gives us x equals negative 1, x equals 1. And so these are our bad numbers, right? So these are the numbers that would give us 0 in our denominator, so they're not in our domain. So our domain in this case is negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. All right, part 2, part B, we want to find our critical numbers. So remember, to find your critical numbers, we look at where f prime of x is undefined. So in this case, f prime of x is going to be undefined whenever the denominator, x squared minus 1 quantity squared, is equal to 0. So that's going to be undefined whenever x equals plus or minus 1. But we know these are not critical numbers since they're not in our domain, right? So these are not critical numbers. So we still have to keep them in mind because they're in our domain also, or they're not in our domain, so they're splitting up the negative infinity to infinity, right? But they're not critical numbers, which means they're not candidates for relative extrema. So then the other piece we have to consider is where f prime of x equals 0. So that's going to equal 0 whenever negative 2x equals 0, right? So then that means x equals 0, dividing by negative 2 on both sides. So x equals 0 is our only critical number. Part C, we want to find the open intervals where f is increasing or decreasing. So remember, from that, what we're checking is the sign of the derivative, f prime of x, on either side of the critical number, x equaling 0, and about, in this case, our values where the domain splits at negative 1 and 1, right? So our discontinuities. So if we set up our intervals, so looking at our number line, if here's my negative infinity to infinity, there's my negative 1 to 1, and here's my 0, right, in between those two. So then we're going to have the intervals negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to positive infinity to check. So we have 4 different intervals we have to check. And remember, from each of these intervals, we want to pick a test point. So on negative infinity to negative 1, I'm going to pick negative 2. Remember, you can pick any values you want to pick as long as it falls in the interval. Negative 1 to 0, I'm going to pick negative 1 half. 0 to 1, I'm going to pick positive 1 half. And 1 to infinity, I'm going to pick 2. And then we're finding, so we know f prime of x is negative 2x over x squared minus 1 quantity squared. And so we're going to plug these 4 test points into that and find the derivative. So f prime of negative 2. So that's negative 2 times negative 2 over negative 2 quantity squared minus 1. So then negative times negative is going to be positive. And our denominator is all squared, so that's going to be positive. Because anytime we square something, it's positive, right? So positive dot positive greater than 0, so f is increasing on this interval. F prime of negative 1 half. So that's negative 2 times negative 1 half over, and I apologize for how small this is. I apparently didn't leave myself enough room here. Over negative 1 half quantity squared minus 1, all that squared. So negative times negative again is positive. And something squared, so our denominator is always positive. Positive divided by positive is greater than 0, so we're increasing. F of positive 1/2, or sorry, f prime of positive 1/2. So that's negative 2 times positive 1/2 over positive 1/2 squared minus 1 quantity squared. So negative times positive in our numerator is going to be negative. And our denominator is always positive since that's something squared. So this is going to be less than 0 because negative divided by positive is going to be negative. So f is decreasing here. And then f prime of 2. So that's negative 2 times 2 all over 2 squared minus 1 quantity squared. So negative times positive is negative over positive because our denominator is always positive, so that's less than 0. So f is decreasing here as well. So we know then f is increasing on the intervals negative infinity to negative 1, union negative 1 to 0, right? Now remember, we can't say that f is increasing on negative infinity to 0 because negative 1 is not in our domain, right? And then f is decreasing on, we found 0 to 1, and then union 1 to infinity. Part D, the open intervals where f is concave up or concave down. And so to find those, now we're looking at our second derivative. So we're going to check where f double prime of x is undefined and f double prime of x is equal to 0. So f double prime of x is undefined when x equals positive negative 1 again. So setting our denominator equal to 0. But again, not in the domain of f, right? So we know these won't be points of inflection. And then f prime of x equal to 0, so f prime is never going to equal 0, right? So if we set 2 times 3x squared plus 1 equal to 0, then the numerator is not equal to 0 in real numbers. So we have a sum of a couple values, so something squared plus 1. So if we were to solve that, so 2 times 3x squared plus 1 equals 0. You get 3x squared plus 1 equals 0 by dividing by 2 on both sides. So then subtract 1, 3x squared equals negative 1, x squared equals negative 1/3, which we know is going to be a complex number. And we only care about real numbers right now. All right, so then all we have to look at is the values where f double prime is splitting on the domain, right? So we're going to look on the intervals in this case. We just have to worry about our domain. So negative infinity to negative 1, negative 1 to 1, 1 to infinity. I'm going to choose the same 2 of the 3 numbers. So my test points in this one, I'm going to still pick negative 2 and positive 2, but then on negative 1 to 1, I'm going to pick 0 because it's an easy number and we can pick it this time. So then f double prime of x is 2 times 3x squared plus 1 over x squared minus 1 to the 3rd power. F double prime of negative 2. So that's going to end up being 2 times 3 times negative 2 squared plus 1 all over negative 2 squared minus 1 to the 3rd power. So then our numerator, so negative 2 squared is positive, positive times 3 is positive, plus 1 is positive times 2 is positive. Our denominator, squaring negative 2 makes it 4. 4 minus 1 is going to be positive. So cubing that's going to be positive. So we have positive divided by positive. So that's greater than 0. So we know it's going to be concave up. Checking 0, so f double prime of 0. 2 times 0 squared plus 1 over 0 squared minus 1 to the third power. So 0 squared 0 plus 1 is positive, times 2 is positive. 0 minus 1 is going to be negative. Cubing that's going to be negative, so we have a positive divided by a negative. So that's less than 0, so concave down. And then my 2, I'm running out of room there, so I'm going to write it up here. F double prime of 2. So that's going to be 2 times 3 times 2 squared plus 1 over 2 squared minus 1 to the third power. So positive squared is positive times positive plus positive times another positive. Numerator is positive. 2 squared is 4 minus 1 is 3, positive 3. So cubing the positive is positive. So greater than 0, so concave up. So we know f is concave up on the intervals negative infinity to negative 1. Union 1 to infinity. So that was our f double prime of negative 2. So we said that was concave up there. So negative infinity to negative 1, union 1 to infinity. And concave down on negative 1 to 1. Alright, relative extrema, so going back to our only critical number, x equaling 0, looking at what's going on with our sign there. So our first derivative, looking back at our work from part C, went from on negative 1 to 0, it was positive, it was increasing, and then 0 to 1 went to decreasing. So in this case, we know we're going to have a relative maximum at, in this case, 0 comma f of 0, which is 0, and then plugging 0 in to f of x. So f of 0 is just 1 over 0 squared minus 1, which is 1 over negative 1 or negative 1. So we have a relative max at 0, negative 1. We have no relative minimum because we have no other critical values, right? Now, it's worth noting, I just looked back at the first derivative test, right? So our work for the first derivative test was on part C. But I also chose to use 0 as a test point in part D, where we were finding the intervals of concavity. So notice, since I used 0, which was also our critical value, right? Then I've also done the work for the second derivative test. So the second derivative was less than 0, which then tells us we have the relative maximum at 0 f of 0. Point of inflection. So in this case, remember that we can't have a point of inflection, right? Because even though we're changing concavity on the interval negative 1 to 1, so it's going from concave up to concave down and then back to concave up, so negative 1 and 1 cannot be points of inflection because they're not in our domain, right? So they have to be in the domain to be a point of inflection. Our y-intercept, so remember to find the y-intercept, you set x equal to 0 and solve for y. So in this case, our y-intercept is 0, negative 1. We've already done the work to find that. Asymptotes, so vertical asymptote, in this case, f of x is already in its simplified form. So we could rewrite this as 1 over x plus 1, x minus 1. And so then negative 1 and 1 in this case, we can't rewrite this function. So we know the limit's not going to exist. So we know that these values are going to be our vertical asymptote. So we have vertical asymptote at the lines x equaling negative 1 and x equaling 1. Horizontal asymptote, so limit as x is approaching infinity of our function, 1 over x squared minus 1. So divide everything by x squared, so this is the limit as x is approaching infinity, 1 over x squared over x squared over x squared minus 1 over x squared. And then using the very useful fact, this becomes the limit as x is approaching infinity of, we evaluated the limit now, so this is no longer limit because we're using our very useful fact. And so now limit as x is approaching infinity, 1 over x squared by the very useful fact is 0. Limit as x is approaching infinity of x squared over x squared is 1. So limit as x is approaching infinity of 1 is 1. Limit as x is approaching infinity, 1 over x squared by the very useful fact is 0. So we have 0 over 1 minus 0, which is just 0 over 1, or 0. So our horizontal asymptote is going to be the line y equals 0. And because we have a horizontal asymptote, we know we have no oblique asymptote or slant asymptote, because we can't have both at the same time. And so now let's put all of this together and sketch our graph. So if I draw my axes in here, and I expect you to label everything. So here's my y-axis, my x-axis, there's my origin. And so going back, usually I start out by plotting my asymptotes first. So we have a vertical asymptote at x equaling positive 1. And at negative 1. We know we have a horizontal asymptote at the line y equals 0, which is our x-axis. So now starting with extrema, so we know we had a relative maximum at 0, negative 1. So there's our relative max. So because it's a relative max, it has to be going from increasing to decreasing between these two asymptotes. So we know we have that. So that's what our graph's going to look like there. And if we look, that matches increasing negative 1 to 0 and then decreasing 0 to 1. So, and then also combining that with the fact that it's concave down on negative 1 to 1. So that all matches. Really, at this point, it's just taking those puzzle pieces that I gave you and putting them together. And then on negative 1 to infinity, what do we know is going on? So we look, negative infinity to negative 1, it's increasing. And it's concave up. So increasing concave up has to look like that. And then for 1 to infinity, we look, it's decreasing, and it's concave up. So decreasing concave up, it's going to have to be up here. So going back to those pieces, and it's going to be, it's going to look like that. So in the end, this is our graph for y equals f of x, whenever f of x is 1 over x squared minus 1.